Hello and welcome back to our introductory course on machine learning. This is going to be the fourth video in Unit 2 and it is going to cover support vector machines. Support vector machines are commonly used throughout machine learning and are an exciting topic that's going to help us expand on some of the scenarios that we learned about in the first couple of videos. And again, this is presented by EDU Onyx. So let's get started. The support vector machine is a new approach for linear classification and regression. It can do both classification and regression, and it's an extension of the linear methods that we've already learned. Before we get started, I'm going to cover some of the reasons why it gets used a lot, and also why these are referred to as kernel machines. So, the support vector machine is popular because, number one, it is a discriminant-based method. Therefore, it isn't computationally expensive, and we can ignore data points that are far away from the class boundaries. So we'll learn more about that later and what it means to ignore data points that are far away from our class boundaries. Secondly, the weight vector can be written in terms of a subset of the training set, and these are known as the support vectors. So after training the parameters of the linear model, the weight vector can be written down in terms of a subset of the training set, which are the so-called support vectors. In classification, these are the cases that are close to the boundary, and as such, knowing them allows knowledge extraction. Those are the uncertain or erroneous cases that lie in the vicinity of the boundary between two classes. Their number gives us an estimate of the generalization error, and as we see below, being able to write the model parameter in terms of a set of instances allows kernelization. So we'll talk about kernelization and kernel machines in one of the following slides. Next, as we will see shortly, the output is written as a sum of the influences of support vectors, and these are given by kernel functions that are application-specific measures of similarity between data instances. These kernel functions allow us to transform the input to another space where a linear or smooth solution is possible. So we're going to see how we can use linear methods to solve nonlinear cases. And finally, kernel-based algorithms are formulated as a convex optimization problem, and there's a single optimum that we can solve for analytically. This is really nice because therefore we don't need more complex model parameters such as heuristics for learning rates, initializations, or to check for convergence and such. So we're going to get analytical solutions out of these as well. And that is generally very nice because it allows us to apply models more quickly and find optimum solutions much easier. So the optimal separating hyperplane, what is it? Let's start again with two classes and use the labels -1 and +1 for the two classes. So we are going to find the weights such that if it is greater than 1, we have our +1 class, and if our model is less than 1, we have our -1 class. And this can be rewritten as seen on the right here. So not only do we want the instances to be on the right side of the hyperplane, but we also want them some distance away for better generalization. Our function on the right here, RT times the transpose of W x of t plus W naught, is greater than or equal to 1 instead of just 0 because we want a margin. We want some distance between the hyperplane and our nearest points. The distance from the hyperplane to the instances closest to it on either side is called the margin, and we want to maximize this for best generalization. So to maximize the margin, we're going to minimize the norm of the vector W such that we get this. And the math to calculate this is beyond the scope of this video and this introductory course, but for now it's worth noting simply that finding the optimal separating hyperplane is going to depend on the norm of the weight vector, and we're trying to minimize that while keeping it subject to our following linear function defined above. So now that we are using the hypothesis class of lines, the optimal separating hyperplane is going to be the one that maximizes the margin, because we can find many that are going to separate them, but we want to maximize this again. And again, the distance to the discriminant from any point depends on the norm of W. Therefore, to maximize the margin, we minimize the norm of our parameters. Furthermore, this is a standard quadratic optimization problem, and it can be solved directly to find our parameters, W and W naught. Then, on both sides of the hyperplane, there will be instances that are 1 over the norm of W away from the hyperplane to give us a total margin of 2 over the norm of W. In previous videos, we also used beta. Again, these are just the weights or the parameters of our linear model that we're trying to optimize. So W naught here again is going to be our bias, similar to what beta naught was before. So once we solve this, we're going to get the support vectors. And again, the support vectors are found using Lagrange multipliers. Lagrange multipliers are outside the scope of this video. However, we can look at what they give us. So using the Lagrange multipliers, we can find the data points that lie on the margin. And the ones that lie on the margin are going to have our function on the top right here, r to the t times the transpose of w x of t plus w naught equal to 1. So they're not greater than 1 here. These are the ones that are going to be equal to 1. And these data points are known as the support vectors and can be used to calculate w naught using the equation you see here at the bottom. So each individual point can be used to solve for W naught here, and then for numerical stability, it is advised that this be done for all support vectors and an average taken. The discriminant thus found is called the support vector machine. So if you really want to dive into the math behind that, you can look up Lagrange multipliers online and how they are applied to find the support vectors in SVMs. However, for now, it's worth noting that only the points that lie on the margin are going to be referred to as support vectors. So let's take a look at example here. We have a two-class example. We have data represented by the pluses and data represented by the points. In the middle, we have an optimal separating hyperplane, which is the solid line. And then on either side of that, we have a dotted line, which is representative of our margin. So we have equal distance for our margin on either side. The points that are circled are going to be the support vectors. These are the points that lie on the margin and are equal to 1 in our previous equations. So you can see this is a great for a two-class example. However, the problems are often much more complex than this, as we've seen in some of our examples in other videos. We don't always have this optimal linear hyperplane that can separate our two classes or multiple classes so well. So let's take a look at what that means. In the non-linear case, we're going to have a slightly different scenario that we need to account for. If the problem is non-linear, instead of trying to fit a non-linear model, what we can do is actually map the problem to a new space by doing a non-linear transformation using suitably chosen basis functions, and then use a linear model in this new space. The linear model in the new space corresponds to a non-linear model in the original space. This approach can be used in both classification and regression problems, and in the special case of classification, it can be used with any scheme. In the particular case of support vector machines, it leads to a lot of different simplifications. So that was a lot of spaces and basis functions. We haven't covered basis functions, so I'm just going to give you a quick definition here. Google will tell you that a basis function in mathematics is an element of a particular basis for a function space. So when I first read that, that was kind of hard for me to follow. So we've got some simplifications below. Every continuous function in the function space can be represented as a linear combination of basis functions, just as every vector in vector space can be represented as a linear combination of basis vectors. So this is similar to a Taylor expansion, however, it's going to be a vector expansion or a linear combination of basis vectors. Alright, so now we move on to the kernel machine. The idea in kernel machines is to replace a complicated inner product between some of our basis functions with a simpler kernel function. So again, remember the goal is to solve a nonlinear problem by mapping it to a higher dimensional space. During that mapping, we're going to run into this inner product of basis functions. What we do is we actually use what's called the kernel trick, and we replace this inner product with a kernel function of this form, where the kernel function is going to be between instances in the original input space. So instead of mapping two instances, in this case x of t and x of s, to the new space and doing a dot product there, we can directly apply the kernel function in the original space. So this implies that if we have the kernel function, we do not need to map it to a new space at all. Actually, for any valid kernel, there exists a corresponding mapping function, but it may be much simpler to simply use our kernel function rather than calculating this inner product and then taking the dot product as well. So in summary, what we're going to do is we're going to replace the features or predictors with a kernel function. So any linear model can be turned into a nonlinear model by applying this trick, what is known as the kernel trick, and that is replacing features with a kernel function. So kernel functions are going to completely eliminate the need to map to a higher dimensional space, and by replacing these features with these nonlinear transformations, we are going to be able to solve linear problems or nonlinear problems with a linear method, with our linear model still. So let's take a look at some common kernels. The most popular general purpose kernel functions are polynomials of a degree q. So these are going to have the following form, and q here is going to be selected by the user. So this could be first degree, second degree. Well, first degree would be linear still, so second degree gives you a nonlinear solution, third degree all the way on up, depending on whatever is best suited to your particular case. So again, this kernel here is simply going to be a nonlinear transformation of your input data, which is the x here, so that we can use our linear methods to find an optimal separating hyperplane, like we did in our first example case. Another common one is a radial basis based on radial basis functions, and these are going to be spherical in nature. This equation specifically defines a spherical kernel where x of t is the center and s, supplied again by the user, defines the radius. So the best values for these should be found by cross-validation. When you have multiple parameters to optimize, it's good to do a two-dimensional optimization using cross-validation with a variety of different parameters. Finally, we also have sigmoidal functions, and sigmoidal functions could be, for example, our hyperbolic tangent, where the hyperbolic tangent has the same shape as a sigmoid, except that it's going to range between -1 and +1 to fit the example of our support vector machine. So let's take a look at how this kernel would be used. We're going to take a look at the polynomial kernel specifically. So this is the same data that we had before. However, now we have the discriminant being defined, the discriminant and margins found by a polynomial kernel of degree 2. So again, the circled instances are the support vectors, and we can see that we are really having a nonlinear solution here, even though we used linear methods to find this. And this is using a polynomial kernel applied to the original features to then use a linear method to solve for the optimal separating hyperplane. So it's also worth noting at this point that you can have application-specific kernels that are tailored to the data that you're working with specifically. Application-specific kernels are probably a little bit outside the scope of an introductory course, but they are worth mentioning because they will be used fairly commonly for more complicated machine learning tasks. So, in summary, SVMs, or support vector machines, are a discriminant-based method that find the optimal separating hyperplane between classes. The optimal separating hyperplane maximizes the margin in order to improve generalization. That margin is there so that when we get new input points, it's more likely to classify them correctly. And then finally, kernel functions can be used to solve nonlinear cases by using linear methods in higher dimensions. So that is support vector machines in a nutshell. In a project later in this unit, we are going to take a look at actually utilizing the support vector machine as well as some other algorithms. And so that will be very exciting, but we will get to that later. This is the 4th video. In the next video, we're going to talk about some other kernel smoothing techniques and basis expansions. So those are going to be some additional techniques that we can use to solve nonlinear cases. Thank you everybody for listening to this presentation.